Well, hello everyone from Math 2200. It's Discrete Mathematics. This is Professor Wenson here with a video on your ZyBooks Section 1.1 titled Propositions and Logical Operations. Alright, so this video is going to be probably a little longer than most of the videos I put up because I'm going to be going through the entire section as a whole. This is kind of like giving you a freebie, right? Just taking you through the entirety of section 1.1. In future videos for other sections, I'm just going to scan things and go over the important stuff and, start you off on certain participation activities and challenge activities, but not do all of them like I'm going to do in this video. Okay. All right. So here I am on the Canvas page for Math 2200. And what you're going to see is, now this is, I'm in the teacher view right now, but you'll be seeing the same modules. Week 1, should be opening up to you. And in week 1, you'll see the week 1 overview, and then you'll see a page for every section that I recommend you cover that week. And this video today I'm going to do on, this video here I'm going to do on section 1.1, propositions and logical operations. When you click on that, it's just going to tell you three things. Read the section in your ZyBooks text. So you're going to have to go to the separate ZyBooks text. Just go to zybooks.com, and hopefully you've subscribed to the text by now and did all that, and you saw all that, how to do that in the week 0 module, and get into the Math 2200 Discrete Mathematics textbook. Right. Oh, and at the time I'm recording this, it looks like some of you have already done this and have already started, right? Because I can see what you're doing in each section here, and you should be able to see this as well. What percentage of the participation activities and what percentage of the challenge activities you have completed, for each section. And when the week is over, all right. So in the beginning of week 2, and I'll do this at the beginning of every week. In week 1, I have 1.1 through 1.6. I recommend you do those sections. Even though not everything is not due until all the ZyBooks activities, I don't have them due for you. You don't have to finish them until the end of the semester, till Sunday, May 9th. But at the beginning of week 2, I will go in and enter grades for you, just based on these percentages I'm seeing. And and that can change, right? So if I enter a 0 for you for section 1.2 or something, for the participation activities for section 1.2, for example, if I enter a 0 for you at the beginning of week 2, that just means you haven't done it yet. It's not going to stay a 0, right? If you finish it later, and I note and you point that out to me, or I see it later, and I'll definitely see it at the end of the semester, because at the end of the semester I'm going to go in and make sure all the grades are correct. But I will week to week be entering the grades for your ZyBooks and your also your assignments, the ones you're going to be submitting to me on paper, through the assignment page, uploading a file. But yeah, but just because you see a 0, right, doesn't mean it's going to stay a 0. Okay. All right. So you have read the section, right? So you go to your open up chapter 1 here. I'm opening section 1.1, propositions and logical operations. That'll eventually open up. Beneath that, you have, while you're reading, do the participation and challenge activities in the section as you read. Now, not every single section has participation activities. Some sections have challenge activities. And you'll notice when they arrive, they'll be participation activities have like an orange color on the box. Challenge activities have a blue color. And as I mentioned, they're all due by 11:59 p.m. on Sunday, May 9th, at the very end of the semester. So if you're unable to get to things this week, you can do it later in the semester at your leisure, whenever you have time. I would highly recommend, though, doing at least an hour of work every day, just so you're not overwhelmed at the end of the semester, right? Just to get some of this stuff done, and work on your the assignment I have for you each week as well. then beneath that, if you'd like to watch some videos from people, on YouTube other than myself, I have put just some, right, just a couple. If you want to find other ones, you can search on your own for the objective that's mentioned here, or search for a topic. But here are just some videos related to the topics brought up in the section. If you'd like to see other videos, like I said, search for the objective on Google or YouTube. So here I just have some topics that are covered in section 1.1 and a video from YouTube related to that topic. Now you can play the video in Canvas or just click on the link and watch it in YouTube. All right. So I have several topics here: truth tables, negation of a proposition, compound propositions, introduction to propositional logic. All right. And every single page for these sections is going to look like this, where it asks you to read the section, do the activities in the section in ZyBooks, and watch some videos if you'd like. And also, just like any other textbook and any other videos you'd be watching, you should probably take notes as well, right? And organize those notes in a fashion that'll make it easier to read later on when you're reviewing. All right. So the rest of this video is just going to be me going through section 1.1. All right, and I'm going to go through this section in detail. All right, like I said, this will be the longest one where I'm going to do all the participation activities in here. There are no challenge activities in this section, so not going to be doing any of those. And on occasion, I'll go to a pen and paper, marker and paper to write out some stuff to show you certain things. All right, and yeah. So here we are, section 1.1, propositions and logical operations, in the chapter on logic. All right, like I said, I'm going to read it all to you here. I'm not going to do this in every video. All right. Logic is the study of formal reasoning. A statement in a spoken language, such as English, is often ambiguous in its meaning. By contrast, a statement in logic always has a well-defined meaning. Right. Logic is important in mathematics for proving theorems. Learn about those later. Logic is also used in computer science in areas such as artificial intelligence for automated reasoning and in designing digital circuits. Logic is useful in any field in which it is important to make precise statements, right? Clear statements. In law, logic can be used to define the implications of a particular law. In medicine, logic can be used to specify precisely the conditions under which a particular diagnosis would apply. All right. The most basic element in logic is a proposition. And then, like in most texts, you'll have bold words, right? Important stuff. A proposition is a statement that is either true or false. All right, it's simply that, a statement that is either true or false. Examples of propositions. There are an infinite number of prime numbers. This is a statement that is either true or false, and in fact, it is true. 17 is an even number. Right, this is a statement that's either true or false, and it is in fact false. Right. Propositions are typically declarative sentences where you're declaring something, stating something that has a truth value to it, is either true or false. For example, the following are not propositions. So here are some English sentences that are not propositions. What time is it? Is that true or false? No, a question is not going to be true or false. It's not a declarative statement. So a question is not a proposition. Right? A question is neither true nor false. Another question, right? Are you awake? That's not a true or false statement. It is a question. Have a nice day. That's just telling someone to have a nice day. There's no truth or falsehood to that. A command is not a proposition. All right, so commands and questions are not propositions. A proposition's truth value is a value indicating whether the proposition is actually true or false. So truth value is simply true or false. When you say the value of a proposition is true, the value of a proposition is false. That's the truth value. A proposition is still a proposition, whether its truth value is known to be true, known to be false, unknown, or a matter of opinion. All right, so whether you know it's true or not, if it can be true or if it can be false, then it's a proposition. Right? So the following are all propositions. 2 plus 2 is 4. Truth value is true. Right? 2 plus 2 is 5 is a proposition. The truth value is false, though. Right? That's not a true statement. Monday will be cloudy. See, this is either true or false, so it's a proposition, but say Monday's in the future, see, will be. So the truth value is unknown at the time, but it can be ascertained later. Right? And then a matter of opinion, but the movie was funny. Well, that's a true statement to some people, and it's a false statement to others, depending on the film and their opinion. But it's still a statement that can be true or false, so it has a truth value, right? All right, now I did complete, you'll see the participation activities with the orange bar before it like this. So you're going to be completing all of these. Now I did this in the week 0 video, my week 0 syllabus video. So that's why this one's filled in orange with the check marks, right? In the upper right hand corner there, that's when you know a participation activity is complete. But I'll still go through these because I flew through them in the syllabus video just to show you what it looks like when an activity is complete. Alright, so here indicate which statements are propositions. Right? 10 is a prime number. Right? Can that be true or false? Well, yeah. And it's false, right? But it can be true or it can be false, so it is a proposition. Right? Shut the door. That's a command, right? You saw that have a nice day earlier. This is neither true nor false. It has no truth value. That's not a proposition. All politicians are dishonest. This is a statement that is true to some, false to others, but it does have a truth value. So it is a proposition. Would you like some cake? Mentioned that earlier, right? A question is not true or false, right? A question has no truth value, so it is not a proposition. Interest rates will rise this year. Again, this is something that could be true. They could rise, or it could be false. They could not rise. But the truth value is unknown. It's something that's going to happen in the future. But there's still a truth value to the statement, possibly. All right, so it is a proposition. Okay. So now we get into certain, now that we know what propositions are, we're going to get into operations involving or using propositions, right? Making what are called compound propositions, which we'll see here in a second. Propositional variables such as lowercase p, q, and r can be used to denote arbitrary, right, random propositions, as in, say, proposition P is the statement January has 31 days. Proposition Q is the statement February has 33 days, right? These are propositions because they can either be true or false, right? P is true, Q is false, right? February does not have 33 days. So usually a proposition will be represented by some lowercase letter. Okay. Now, a compound proposition is like a compound sentence, right? Putting two statements together, two propositions together, is created by connecting individual propositions with logical operations. A logical operation combines propositions using a particular composition rule. For example, the conjunction operation is denoted by this triangular wedge here. Looks like almost like a caret, right? That symbol. The proposition P in conjunction with Q is read P and Q. So when you see this conjunction operation symbol, you can think of it as like the word and, right? And is called the conjunction of P and Q. Right? So P and Q, or the conjunction of P and Q, a statement like this is true if both P is true and Q is true, right? So the only time a conjunction is true is if both propositions are true at the same time, right? If one of them is false or both of them are false, then the whole conjunction, as an entire statement is false, right? Using the definitions for P and Q, or the conjunction of P and Q given above, the proposition P and Q is expressed in English as, so here's again statement P, proposition Q. The proposition P and Q is simply January has 31 days, that's P, and February has 33 days, that's Q. Proposition P's truth value is true, right? January does have 31 days. Proposition Q's truth value is false, right? February does not have 33 days. The compound proposition, therefore, right, P and Q, is false, because it's not the case that both propositions are true, right? This entire statement, P and Q, is false because P and Q are not both true, right? Q was false. All right, so I'm going to actually write this out by hand, all right, to show you a truth table. You're going to be making lots of truth tables in this first chapter. A truth table shows the truth value of a compound proposition for every possible combination of truth values for the variables contained in the compound proposition. Every row in the truth table shows a particular truth value for each variable, along with the compound proposition's corresponding truth value. Below is in this activity here is a table, a truth table for P and Q, where they're going to use the capital T to represent true and F to represent false. Now, this is one of those animations where you hit start and then it shows you, hey, P and Q is true only when both P and Q are true. So they show you that here in this truth table. So I've got statement P, statement Q. When statement P is true and statement Q is true, the statement P and Q in the conjunction is also true. And then I hit play some more for the second. See how it shows you how many of the animations there are. And then P and Q is false for all other combinations, right? When P is true and Q is false, like in the example up here with January and February, when P is Q and Q is false, P and Q, the conjunction, is a false statement. When P is false and Q is true, P and Q is false. When they're both false, P and Q is false. All right. Now I'm going to go to a paper and show you how to, you can tell how to make it, but I'm going to show you how I would draw it out, a truth table. Okay, so on a piece of paper here, I write the individual propositions for a conjunction. There's only two of them. One was called P, so I make a column for P. The other was called Q, right? So I make a column for Q. Right? So I like making columns for the individual propositions first before getting into the compound proposition columns. And since there are two propositions, the number of rows you're going to have is 2 times 2. Is going to be 4. For every proposition, you're doubling the number of rows you need to make, because the possible values for P are T or F, right? There's 2 choices for P times the 2 choices for F, giving me a total of 4 possibilities here, 4 combinations of truth values. So if there were 3, propositions P, Q, and R, then there would be 2 times 2 times 2. There'd be 8 different rows, 8 different combinations of truth values I would have to make. But here there's only 2 propositions, so only 4 rows. All right, so down the first column, I know I'm going to make 4 rows, so I'm going to do half true, half false. And I always do that for the first proposition. Half true, the first half true, the second half false. So blocks of 2. And then I cut blocks of 2 in half and do blocks of 1. So down the Q column, I'll do, instead of 2 trues then 2 falses, I'll do blocks of 1. Cut that in half. 1, then 1, then 1, then 1. So 1 true, then 1 false. Then 1 true, then 1 false. And here I get all 4 possible combinations of truth values for 2 different propositions. They're both true. P is true, Q is false. P is false, Q is true. And they're both false. All right, then added to this, another column. And here we're doing the conjunction operation, which is the and. Right, combining 2 statements, 2 propositions with the word and. So P and Q, right? That this symbol will mean and. If both the propositions are true, right? This is the conjunction is only true, as you've seen, when both individual propositions are true, when both are true at the same time. So in this situation, when both P and Q are true, P and Q, that statement, is also true. And then the rest of the time, the conjunction is false, because both P and Q are not true at the same time. At least one of them is false. So the conjunction would be false in this situation, false in this situation, and false in this situation. All right, and again, this is called the truth table for a conjunction of 2 propositions. Okay, and like I said, we'll be doing a lot of these for Chapter 1 on logic. All right. So again, play through the animation. Right. Next, we have different ways to express a conjunction in English, right? So instead of using the word and in English, you could express that 2 things are happening at the same time, this and that, with different words. So an example, right? Define the propositional variables P and H as these. P is the statement, the sauce looks disgusting. H is the proposition, the statement, the sauce tastes delicious. So you could say, P and H for a conjunction, right? The sauce looks disgusting and tastes delicious. P but H, right? The sauce looks disgusting but tastes delicious. That still means that they're both happening, right? So it's still like an and, despite the fact that P, comma H, right? Despite the fact that the sauce looks disgusting, it still tastes delicious, right? So again, it still kind of implies that both are happening, that P and H are happening. And although although the sauce looks disgusting, it tastes delicious. Again, any statement that would imply that 2 things are happening at the same time is a conjunction, right? An and statement. But for the most part, I'm going to be using the word and. Okay. All right. Next, we have the disjunction operation, which is for the word or, and the symbol for it. Right. The disjunction operation is denoted by, it's the same symbol as conjunction but flipped over. Just flip it over, make it like a V. Right. The proposition P or Q, right, is read P or Q, right, or the disjunction of P and Q. P or Q is true if either one of P or Q is true. So like, or if both are true. Right. So P or Q is true if either P is true, or Q is true, or both are true. So sometimes this is referred to as the inclusive or. It's including the scenario when both are true as well. So P is true, or Q is true, or both, right? Or including both. We'll see the words inclusive or coming up in a bit. So yeah, the proposition P or Q is false only if both P and Q are false, right? If neither one is true, then the whole disjunction statement is false. So using the same P and Q from the example above, P or Q would be the statement January has 31 days or February has 33. Now when it was P and Q, it was a false statement because of the fact that Q was false. But P or Q, this statement is true because at least one of them is true, right? P is true. January has 31 days. So this whole statement, January has 31 days or February has 33 days, as a whole is a true statement. And they say that here. All right, and you play the animation for how to make the truth table for a disjunction for the or statement. Okay, which I'll play it, and again I'm just going to watch this, and then I'm going to go to a piece of paper and do it as well by hand, because you should be able to make these by hand, especially when you're doing the assignments that you're going to be uploading to me. Those are going to be on paper, written out by hand. All right. So here I am back on a piece of paper. So how would I? So again, I have this is for a disjunction, or the or, and this is the inclusive or. All right, in the inclusive or, meaning either one or the other or both can be true. So again, two statements. I have two propositions. And since there are only two propositions, right, 2 times 2 is 4. 2 choices each. There'll be 4 rows, and I'll cut the first one in half, do half trues, half falses. 2 trues, 2 falses, and these were blocks of 2 trues, 2 falses. And then for the next column, I break it into blocks, and I cut that in half and do blocks of 1 true, 1 false, 1 true, 1 false. And there's every single possible scenario, every possible combination of truth values for 2 propositions. And then the third column, I'm going to do the disjunction, P, and again it's upside down, it's like a V shape. All right, just flip the conjunction symbol over, and this is P or Q. Right. And a statement P or Q is true when P is true, or when Q is true, or when both are true. So here both are true, so the disjunction is true. Here P is true, so the disjunction is true. Here Q is true, so the disjunction is true. And in this last scenario, when neither P nor Q are true, the disjunction is false. So true, 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 false, all the different possibilities there. And that's the truth table for a disjunction, P or Q. All right. And I mentioned, now there's two different ways you can look at the word or. Right? Ambiguity of the word or in English. The meaning of the word or in common English depends on context. Often, when the word or is used in English, the intended meaning is that one or the other of the two things is true, but not both. All right, so we have to talk about that. We just talked about the one is true or the other is true, or both, right? The inclusive or. One would normally understand the sentence, Lucy is going to the park or the movie, right, to mean that Lucy is either going to the park or is going to the movie, but not both. Such an either or meaning corresponds to the exclusive or operation in logic, right, which is a different or than the one I just showed you. The one up here, the disjunction, is the inclusive or that's mentioned here. The exclusive or of P and Q evaluates to true is a true statement when P is true and Q is false, or when Q is true and P is false. So when P is true or when Q is true, but not when both are true. All right. That's the exclusive or. Like I said earlier, what we just talked about was the inclusive or. The inclusive or operation is the same as the disjunction operation and is true when one or both of the propositions are true. Right? Okay, so, and we'll get some symbols for that in a second. Now let's take a look. Right, so here, participation activity, not completed yet, right? Indicate whether each statement is true or false. In each case, use the inclusive or, so the disjunction, like we just saw. So when one statement, one is true or the other is true or both. So here the statement is 4 is an even number or 4 is a prime number. Well, one of them is true, right? 4 is an even number, so the statement is true when we're talking about inclusive OR. As long as at least one of the statements is true, the OR statement is true. 2, 5 is a prime number or 3 is a prime number. Now here both are true, and if we're talking inclusive OR, that's fine, then the statement is true. Exclusive OR, that would be considered a false statement. You can't have things in with the exclusive OR. You can't have two things being true at the same time. 2 is a negative number, which is false, or negative 3 is a positive number, which is also false. So here both are false. This is a false statement. And now the activity is complete. I move on. All right, now we get to this, a new symbol, a new operation. This is for the exclusive OR. All right, so please understand the difference. Right? Disjunction inclusive OR was the symbol we just saw that looked like a V. The exclusive OR operation is usually denoted with the symbol, it looks like a plus sign with a circle around it. In this book, in other books I've seen the V with an underline, but in this book it's a plus sign with a circle around it. The proposition P or Q, this is again the exclusive OR, is true if exactly one of the propositions is true, but not both. All right. So let's fill in the truth table. So I'm going to again do this on a piece of paper. All right, so this was, again, this is the inclusive OR, disjunction. Here's the exclusive OR, where I exclude the possibility that they're both true. All right. All right. So again, two propositions, P and Q, four rows. Again, 2 trues, 2 falses. Down the P column, true, false. Down the Q column to get all possible combinations of truth values for P and Q. And then I'm doing the P or Q, right? The exclusive OR. Again, this is only going to be a true statement if P is true or Q is true, but not both. It's not considered a true statement when they're both true. So in this first scenario, when they're both true, this exclusive OR statement is false. Okay. Then here P is true, but Q is not, so the exclusive OR will be a true statement in that sense. This one, Q is true, but P is not, so again, exactly one of them is true, making the exclusive OR statement a true statement. And then when they're both false, it's just like the other one, it's a false statement. So there's the possible truth values of an exclusive OR compound proposition. All right. So keeping that in mind, let's go back here and again, let's complete this participation activity. I already did this. It's false for number 1. Right. True for number 2, true for number 3, and false for number 4. Wonderful, and I got them all correct, and now the activity is complete. And then under what conditions do the logical expressions, P or Q, exclusive OR, and P or Q, inclusive OR, disjunction, have different truth values? Right. So let's go back. You can probably already tell me, but look at these here. Right. On the left, the truth table set up, the P and Q columns are exactly the same. Right. The P and Q columns are exactly the same. Look at the P or Q with the disjunction versus the P or Q with the exclusive OR. See, the second, the third, and the fourth rows are all the same, true, true, false. It's in the first scenario when they're different in the first row, and that's when both P and Q are true. Right? When both P and Q are true, this P or Q is different, has a different truth value than this P or Q, right? Inclusive OR versus exclusive OR. So when both P and Q are true, they have different truth values. All right. Then we have another animation. Now this is a new operation. right? And we talked about disjunction, conjunction. Now we have the negation, right? The negation operation acts on just one proposition and has the effect of reversing the truth value, right? So the negation of proposition P is denoted by this. It's like a little kind of sideways, backwards L looking thing. You'll see me draw it. And is read as not P, right? So you have P and not P, or the negation of P. Since the negation operation only acts on a single proposition, its truth table only has 2 rows, right? Because only a single proposition, as you see here, only has 2 possible outcomes, right? When there were 2 propositions, you had 4 rows, 2 times 2. And as I mentioned earlier, when you have 3 propositions, P, Q, and R, right, you'd have 8 rows, 2 times 2 times 2. It's basically 2 raised to whatever number of propositions you have. That's how many rows your truth table will be. All right, so you start, play this out. Very simple to make, and again, I'm going to make it on a piece of paper. The animation's complete, and it says it's done. Great. All right. So again, another truth table, but this time for another operation called the negation, which is the word not. All right. So you negate just a single proposition. All right. So if I have one proposition, it's either true or it is false. And then this like little sideways L thing, not P. Now I've also seen, okay, in case you're watching videos online, I've also seen this written as like not P with a little tilde, or P bar like that, or P with an apostrophe. I've seen every single one of these mean not P, right? So it depends on who you're talking to, what book you're looking at, what video you're watching. But in our book, in the ZyBooks, it's this little like backwards sideways L here, not P. And if whenever P is true, not P is false. And whenever P is false, not P would be true, right? It's just simply reversing, doing the opposite truth value. Very simple to make the negation truth table. Okay, and now let's apply some of these operations. All right. So they're telling us here, assume propositions P, Q, and R have the following truth values. So P is true, Q is true, R is false. All right, I'm actually going to do this on paper. All right. So we're given the value of some proposition P is true. The truth value of a proposition called Q is true. And the proposition called R is a false statement. All right, so we're given these facts. Right? Number 1 there is what's the truth value of P and Q? Remember, this is that conjunction. So this is, P is true and Q is a true statement. And remember, a conjunction is true when both the P and Q are true, when both statements are true. So that was number 1. P and Q is true. Number 2, not R. So R is some false statement. So this is not a false statement, which would be a true statement. So the truth value of not R would be true. Number 3 in this participation activity is P and R. Again, P is a true statement and R is a false statement. Remember, the conjunction is only true when both are true, like in number 1. So this is a false statement. This has a truth value that is false. Number 4, P or R, and it's the inclusive or, right? The disjunction that we saw, not the plus sign with the circle. So P is a true statement, and or, and then R is a false statement. Remember that the disjunction, the inclusive or, was true if either one of them was true, even both of them. Right? So this is a true statement, has a true truth value. And the last one here in this activity is P or Q, and this is true or true. And now if this was the exclusive or, this would be a false statement, remember, because they're both true. The exclusive or was only true when exactly one of them is true, but the inclusive or, the disjunction, is true if either one or both are true. So this is a true statement. So if true, true, false, true, true. Going back to the activity. All right, so true, true, false, true. I put true, I meant false, right? True, true. Great, and then the activity is complete. I move on, and then there's an example here. I'll let you read that. And then we have additional exercises. Now, additional exercises, you're going to see back in the week 1 module. Back in the week 1 module, you should see it. And every week, I'll have a new assignment for you on the sections that I recommend from that week. All right, and all these assignments are going to be made up of additional exercises that are at the ends of these sections. And I'm not having you do all of them, just some of them. So like for section 1.1, number 1.1.1, 1.1.2, 1.1.3, and 1.1.4, you're going to have to write out. Now there are parts to these, right? So when I say 1.1.1, I mean all the parts. Most of these are, is it true or false, or is it a proposition or not, or write its negation, right? Won't take too long. So it looks like, oh yeah, there's 10 of these, but they won't take that long. 1.1.2 has several parts. 1.1.3 has, again, not very difficult though, because and you can see the solutions. The solutions are available to you to see. Just click on the eyeball or whatever. I'm just going to be great. Remember, when you submit an assignment to me, I'm just going to be grading those assignments on completion. Right? See the work that you did, and not necessarily is your solution correct, because you can always check to see if you're right here. Try to do it before you look at the solution, please. Actually learn something, because you're going to need to know how to do stuff for the few exams that I have for you. The exams you're not going to see solutions to, right? You'll have to know how to do them. And I didn't assign all of them. Well, I did for this section, 111 through 114. But I don't assign every single problem. So in other sections, you might want to also do the ones I didn't assign, just for extra practice. Okay. All right, so that was me going through section 1.1. I hope it was informative. Hope you saw how to make some truth tables a little bit. And again, truth tables will be made in a lot of other videos for chapter 1. So if you didn't get it here, you're going to see a lot more later. And as I was mentioning at the beginning of the video, in the rest of the sections from here on out, I'm not going to do every participation activity. I'm not going to complete all of them. I'm just going to start you off on a few of them. And same thing with the challenge activities. I'm not going to do all the problems. I'm just going to do one, maybe two. Less. I'm going to try to do up to half, but no more than half of them for you, and get you started. Give you a guide. So the next videos, this will probably be one of the longer videos, all right? Unless the topic is heavy, if the topic is difficult, might take a little longer to do certain things, but yeah. So and I'm also not going to read out loud all the sentences. All right. So hopefully this was informative. You can use it as a nice little guide. I mean, I basically just gave you a freebie. I took you through 1.1. And thanks for watching, and keep going on through 1.1 through 1.6 in week 1 here, and if you'd like to work ahead, you can always do that, right? Every section is available for you to do the ZyBooks activities right now. All right, and thank you very much for watching.